Good morning everyone. My name is Pallavi Jaiswal. Today I am going to explain the topic Theory of Equilibrium, Stable and Unstable Equilibrium, Application of Theory of Equilibrium on Strings, System of Forces and Virtual Work. Now let us understand what is equilibrium. It is a state of balance, especially between forces or influences that are working in opposite ways. There are three types of equilibrium. First is stable equilibrium, second is unstable equilibrium, and third is neutral equilibrium. So, the first, stable equilibrium. A system is said to be in stable equilibrium if, when displaced from equilibrium, it experiences a net force or torque in a direction opposite to the direction of displacement. Now, unstable equilibrium. A system is in unstable equilibrium if, when displaced, it experiences a net force or torque in the same direction as the displacement from equilibrium. Now, neutral equilibrium. A system is in neutral equilibrium if its equilibrium is independent of displacements from its original position. Now, let us understand the concept of stability or instability of body with its center of gravity. There are three cases arises. The case 1 is if the center of gravity lies on the vertical line through the point of contact and it is below the geometric center of the sphere as shown in the figure, and the sphere is slightly displaced, then it tends to come back to its original position of rest. Then this position is stable equilibrium. Now case 2. If the center of gravity lies on the vertical line through the point of contact and it is above the geometric center of the sphere as shown in the figure, and the sphere is slightly displaced, then it tends to go back away from its original position of rest. Then this position is unstable equilibrium. Now case 3. If the center of gravity lies on the vertical line through the point of contact and coincides with the geometric center of the sphere and is slightly displaced, then it will remain in equilibrium. Then this position is known as neutral equilibrium. Now example of equilibrium. The first example of stable equilibrium. When a book lying on the table, tilt the book slightly above its one edge by lifting it from the opposite side. It will return to its previous position when set free. When a body is in stable equilibrium, its center of gravity is at lowest position. When it is tilted, its center of gravity rises. It returns to its stable equilibrium as long as the center of gravity acts through the base of the body. Now example of unstable equilibrium. Take a pencil and try to keep it in the vertical position on its tip. Whenever you will leave it, the pencil topples over above its tip and falls down. Hence, it is an unstable equilibrium. A body may be made to stay only for a moment. Thus, the body is in unstable equilibrium. Now the conditions of stability of body with 1 degree of freedom when the work done is W is equals to function of theta. For the stability equilibrium, we have F dash theta naught is equals to 0, F double dash theta naught is less than 0, which implies that stability of equilibrium for W is maximum at theta is equals to theta naught. Similarly, for the unstable equilibrium, we have F dash theta naught is equals to 0 and F double dash theta naught greater than 0, which implies that stability of equilibrium for W here minimum at theta is equals to theta naught. Now the general conditions for stability of a body resting on another one. If the upper body has a plane face in contact with the lower body, then radius is equals to infinity. So we have stable equilibrium for h is less than r and unstable equilibrium for h greater than r. Here small r and capital R are the radius of different spheres. If the lower body has a plane surface, then r is equals to infinity. So we have stable equilibrium for h less than r and unstable equilibrium for h greater than r. If the lowest surface is concave, then r is negative and we have a stable equilibrium for 1 by h is greater than in the bracket 1 by small r minus 1 by capital R. For unstable equilibrium, we have 1 by h is less than 1 by r minus 1 by capital R. Now our next topic is application of theory of equilibrium on strings. In the figure you can see that there are 2 points P and Q. We have to check it is in equilibrium or not. For this, let P x, y and Q x plus del x, y plus del y are two neighboring points on the curve formed by the string. Here AP is equals to S, AQ is equals to S plus del S, arc PQ is equals to del x. The tangent at P and Q making an angle psi and psi plus del psi with x-axis. The tension at P and Q are T, T plus del T respectively. Let M be the mass per unit length of string. Here x and y are component of forces per unit mass of the string parallel to the axis. So the components of forces on PQ parallel to axis are M del x and M del s y. Now the resolved part of T parallel to axis are T cos psi and T sin psi. Then we have T cos psi is equals to T dx upon ds, which is equals to f of s. The resolved part of T plus del T along x-axis will be f s plus del s is equals to function of s plus del s f dash s plus del s square upon 2 factorial into f double dash s plus so on. Now component of T along x-axis will be component of external forces along x-axis and component of T plus del T along x-axis. So we will find out T dx upon ds is equals to m del s into x plus T dx upon ds plus del s dot d by ds in the bracket T dx by ds. Now m del s into x plus del s into d by ds in the bracket T dx by dx will be 0. Dividing by del s we get d by ds T dx by ds plus mx is equals to 0. In similar way we can find along y axis. Now we get d by ds in the bracket T dy by ds plus my is equals to 0. From equation 1 and 2 we get T d2x by ds square plus dt by ds into dx by ds plus mx is equals to 0, and another equation will be T d2y by ds square plus dt by ds into dy by ds plus my is equals to 0. Multiplying the equations by dx by ds and dy by ds and adding, we will get T dx by ds into d square x upon ds square plus dt by s into dx upon ds whole square plus mx dx by ds plus t dy by ds into d2y by ds square plus dt by ds in the bracket dy by ds whole square plus my dy by ds is equals to 0. On simplifying this equation, we will get the below equation. We know that dx upon ds whole square plus dy by ds whole square is equals to 1. We will put in this above equation and get 2 ds by ds into d2x upon dx square plus 2 dy by ds into d2y by ds square, which is equals to 0. Now t into 0 plus dt by ds into 1 plus m in the bracket x dx by dx plus y dy by ds is equals to 0. We will get dt is equals to minus m x dx plus y dy. On integrating, we will receive t is equals to c minus m integration of x dx plus y dy, which is the required equation of equilibrium of a string in a plane under the action of given forces. Now our next topic is system of forces. A force system is the collection of forces acting at the specific locations. Thus, the set of forces shown on any free body diagram make up a force system. Force system is simply a term used to describe a group of forces. There are two types of force system: coplanar forces and non-coplanar forces. Coplanar forces further divide into collinear forces, parallel forces, concurrent forces, and non-concurrent forces, whereas non-coplanar forces divided into parallel forces, concurrent forces, and non-concurrent forces. Now the application of theory of equilibrium on system of forces. If the forces F1, F2 till Fn are acting at point A1, A2 till An respectively on a body, so we can reduce the system into single forces are acting at an arbitrary point O and couple having momentum g whose axis pass through O. Then we have R is equals to summation I is equals to 1 till n Fi, and G will be summation I is equals to 1 n Ai x F1, where Ai is the position vector of Ai. For the equilibrium of body, we have R is equals to 0 and G is equals to 0. If Fi has component xi by I and zi, then Fi can be written as I cap xi plus j cap yi plus k cap zi. Let small ai is equals to I cap small xi plus j cap small yi plus small k cap zi. Then we have, after substituting the values, we get summation I is equals to 1 till n Fi is equals to 0, which implies summation I is equals to 1 till n I cap xi plus j cap capital yi plus k cap capital zi is equals to 0, which implies I cap summation I is equals to 1 till n xi plus j summation I is equals to 1 till n yi plus k cap summation I is equals to 1 and ji, which is equals to 0. We know that x is equals to 0, y is equals to 0, z is equals to 0, where x is summation of I is equals to 1 till n xi, similarly y and z. So having the cross product of ai cross fi, we get I cap, j cap, k cap. In the second line we will write xi, yi, zi. In the third line we will write capital xi, capital yi, capital ji. On having the cross product, we will get I cap small y I capital j I minus z I y I plus j cap small z I capital xi minus small xi capital zi plus k cap small xi yi minus small yi capital xi. Now after adding the summation, we will get summation I is equals to 1 and the given equation we will find earlier and opening it and then equating it to 0. Now we will suppose summation I is equals to 1 till n small yi capital zi minus small zi capital yi is equals to L, and summation I is equals to 1 n small zi capital xi minus small xi capital zi is equals to m, and respectively summation I is equals to 1 till n small xi capital yi minus small yi capital xi is equals to n. Then we have I cap L plus j cap m plus k cap n is equals to 0. From this we can conclude that L is equals to 0, m is equals to 0 and n is equals to 0. From equation 3 and 4 we get x is equals to 0, y is equals to 0, z equals to 0, L is equals to 0, m is equals to 0 and n is equals to 0. These are the necessary and sufficient conditions for the equilibrium. Now our next topic is Poinsott's central axis. It's defined as a line through a rigid body which is parallel to the vector sum F of a system of forces acting on the body, and which is located so that the system of forces is equivalent to the force F applied anywhere along the line, plus a couple whose torque is equal to the component of the total torque T exerted by the system in the direction F. In the given diagram, we can see that the line O dash A dash, i.e. the axis of single couple, and the line of action of single force R means the resultant of the system of force. This line is known as Poinsott's central axis. Now our next topic is virtual work. Its principle is virtual work is the work done by a real force acting through a virtual displacement or virtual acting through a real displacement. The necessary and sufficient condition that a particle acted upon by a number of coplanar forces be in equilibrium is that the sum of virtual work done by the forces in the small displacement consistent with the geometrical conditions of the system is zero. On resolving the force, we can see that F1 is related to x1 and y1, F2 is related to x2 and y2, till Fn related to xn and yn. Virtual work done by the force F1, F2 till Fn are alpha x1 plus beta y1 and alpha x2 plus beta y2, alpha x3 plus beta y3 till alpha xn plus beta yn. So alpha x1 plus beta y1 plus alpha x2 plus beta y2 till alpha xn plus beta yn will be 0. In simple way we can write it alpha summation x plus beta summation y is equals to 0. But we know that from the theory of forces that summation of x is 0 and summation of y is 0. So we will assume the new position of O dash, which will be alpha dash comma beta. So from after putting these points we will get alpha dash summation of x plus beta summation of y is equals to 0. Now subtracting equation 2 from equation 1, we will get alpha minus alpha dash summation x is equals to 0. We know that summation x is equals to 0 because alpha minus alpha dash can never be 0. In similar way, we can prove that summation of y is equals to 0. Hence, it is clearing the definition that in equilibrium, the sum of virtual work done by the forces in a small displacement with the geometrical conditions of the system is 0. Now our last topic is application of theory of equilibrium on virtual work. If a system of coplanar forces acting upon a body keep the body in equilibrium, and if the body be given a slight virtual displacement consistent with the geometrical conditions of the system, then the algebraic sum of the virtual work done by the forces is 0. Conversely, if the algebraic sum is 0, then the forces will be in equilibrium. In mathematical way, we can express the forces to be in equilibrium as summation of x1 is equals to 0, summation of y1 is equals to 0, and summation of small x1 capital Y1 minus small y1 capital X1 will be 0. These are the necessary conditions for the forces to be in equilibrium. Thank you for listening my presentation.